In this video, we will give a look to the option provided by Paratie Plus to model excavation into over-consolidated clays in undrained conditions. When you have to design an excavation in a clay material, you normally assume that the soil reacts in undrained condition. We will review this concept very briefly. However, we must anticipate that this assumption should be carefully examined and accepted by the designer in order to prevent unexpected riskful conditions that may jeopardize any structures around the excavation. With Paratie Plus, we can make a quite simple yet effective analysis of such problems very simply. What a designer has to ask to himself is to guess whether undrained conditions are appropriate for his soil for that problem, and if the lifetime of the structure or the retaining wall is sufficiently short enough to ensure that such undrained condition holds during all the required period. Otherwise, more sophisticated, more complex calculations should be done. And also, a design question is how to deal with the watering, so how to remove the water in these conditions. So, first of all, let's give some statement, some definition of what we mean as undrained behavior. Essentially, in soil mechanics, undrained behavior is a behavior of soil in which there is some fluid, normally water, inside the void that cannot seep away when the soil is deformed. And as long as the fluid is almost incompressible, this condition is as the consequences to provide a constraint in how the soil deforms, so preventing to reduce the volume. So a soil in undrained condition, of course, may deform, but at constant volume. This constraint may have beneficial or also detrimental effects on soil resistance. We will discuss briefly this one. Undrained conditions are typical for clay materials and for soils in which there is a relevant part of clays and silts when we consider short-term conditions. Of course, in this representation that is quite effective, we see that we put in one direction the parameter that is relevant in this case, that is the soil permeability, that is very low for clay and for silts and becomes quite high for coarse material. And on the other axis, we put the velocity of loading or the rating of loading. And we see that for very low application of loading, any soils goes very quickly to drained conditions, so the water can seep away from the volume and hydrostatic conditions are restored. Whereas, as long as the rate of deformation increase, we may have for fine soils, we may have normally initially undrained condition, and then whereas for sandy soils, drain conditions are also applicable to normal construction times, whereas when there is a very fast application of loading, even sands and even gravels and sometimes may undergo undrained condition. This is the case, for example, may have the effect of liquefaction. That is a typical effect for loose sands in seismic condition. But for retaining walls in clay condition, we are here, or almost here in this situation, and normally we may have we may consider that undrained condition hold, but we may exceed sometimes the time where the structure may stay in this condition, and so we may go to undrained condition. So as I said, this constraint to soil deformation may have may provide in some cases some beneficial effect, and in other cases may be detrimental. So we can, just taking a look to clay, we can say that generally speaking, clays, normal consolidated clay with very small shear strength capacity, behave better under drained conditions. So undrained conditions that occur at the very just after the application of loading may be quite dangerous. On the contrary, very highly over-consolidated clays that in the past have been severely loaded behave better and just after the application of loading. So undrained conditions are beneficial, and in that case, on the contrary, long-term conditions in where this effect vanishes may be a concern to be carefully considered in design. How can we describe undrained condition in soil mechanics? There are essentially two practical methods. One method is just to do all the calculation considering total stress. In other words, the stress, the vertical, for example, vertical or lateral stress, not subdividing the effective part from the pore pressures. And in this approach, accordingly, the soil strength is given in terms of undrained shear strength, that is normally named SU or CU, which gives a yield condition in terms of total stresses. And this is also done for stiffness parameters. In this framework that is traditional, pore pressures are not computed because they are automatically incorporated in the calculation of total stress. And they may be estimated following some proposal, like using the A and B pore pressure parameter proposed by Dr. Skempton. There is also a more advanced method that I call method number 2, in which everything, the resistance of soil, is described in terms of effective stress part, and so the soil strength is related to the effective stress parameters like the friction angle or the apparent cohesion, if any, that govern the failure of condition. And also the stiffness of the soil is related to drained soil moduli. Undrained conditions are incorporated by adding a constraint, internal constraint, and everything works if the model is appropriately formulated. And in this kind of approach, we can keep track of both effective stress and pore pressure variation along any stress paths. These two methods can be compared, and we can see that method 1 is the traditional way of doing, and is practically the only way we can adopt when we want to do hand calculation. And there is, in my opinion, also another word of this method is that it is quite, I don't want to say simple, but quite ordinary to calculate, to determine the shear strength capacity, undrained shear strength capacity by means of in situ testing like CPT testing or NSPT testing, along with some very familiar, very usually and well established correlations. Of course, in this method, it's very difficult to study long-term conditions because we cannot know directly how the pore pressure evolved during unloading, during undrained parts. And also, it is also very important to select appropriate value for undrained shear strength. That is not a material parameter, but it is something more complex, and we will discuss later. In method 2, of course, we have a more complex calculation tool must be available, and normally this can be done only with the numerical analysis, like finite element analysis and so on. And because you have to do the calculation considering the coupling of the two effects. And also we have to calculate the effective parameters that cannot normally be captured by in situ testing, but lab testing are normally necessary, like triaxial testing and so on. But in this case, in principle, everything can be calculated, and also we can calculate also what happens when the undrained condition vanish, and what is normally said in soil mechanics, there is the consolidation of soil. Even if we do the calculation with the hand schemes and so on, and use method 1, it is important to understand that actually what is the more physical approach is method 2. So it is important to have some knowledge of both methods. This can provide us some very general statement that may be valuable also when we use method 1. Namely, it is important to remember that the undrained shear strength is not an intrinsic parameters of soil, but depend of any soil in that condition that are in the field, and also on the geological history that soil experienced in the past. So it is important also to remember that the higher are the past effective load going over the soil, the higher will be the actual undrained shear strength. And also the undrained shear strength is not just one value for a soil. In other words, there may be different undrained shear strength depending on the expected stress path in which the different zones on the soil will follow during excavations. And in some cases, undrained shear strength must be very carefully examined by experts when there are some situations in which there may be some very apparently high values that actually cannot be taken into account because they may have sudden and brittle failures of soil and drop down of resistance due to some, for example, chemical bonds and so on that are very, very brittle and unstable. This is a special effect that we don't consider in this presentation and even in Paratie Plus, but it's something that a designer must keep in mind. When we consider a clay formation, we can quite simply realize whether a soil is normally consolidated or over-consolidated by, for example, using SFT testing. If the soil, if the cone penetration, the tip penetration has a pattern like this, in which there is an almost linear increase along with depth, it means that the over-consolidation, the soil is essentially normally consolidated. Whereas in this case, when there is an initial value of CPT that may even reduce with depth or be kept constant, in that case it is typical for an over-consolidated soil. And these are the undrained shear strength profiles for these two kinds of soils. We see that also the undrained shear strength is essentially as a linear increase with depth for a normally consolidated soil, whereas it may be constant or have a more complex pattern for over-consolidated soil. Of course, the undrained shear strengths for the same soil under two different geological histories reveal that the undrained soil has a much higher undrained shear strength, especially in the surface shallow zone. So how can we do the calculation with Paratie Plus? Essentially, very briefly, we can say that both methods are possible. With method 1, we simply assign the undrained shear strength and some undrained elastic modulus varying with depth and for all the clay materials, and we must simply select an option in which we say that everything must be done only following total stress path only. This is in analysis tool property tool dialog box. It is simply we have simply to check this option, and so everything will be done very simply considering only undrained parameter. Of course, it will be no longer possible to switch to drain conditions. So Paratie will do all the calculation with considering total stress components. However, at the very beginning of the analysis, the starting point of analysis assume that from the very beginning there were, let's say in the past, everything was consolidated. So the initial total stress are initialized, assuming that there were drain condition and using these correlations. Method 2 will be discussed more in details in a forthcoming video, but it's also possible in Paratie Plus because there is a special constitutive law in which we can give the resistance of a clay soils in terms of constant volume friction angle and a peak friction angle, as well as an apparent limit for undrained shear strengths for all the clay. And in this case, we must uncheck the total stress path only option, very simply. Then, what is more important, we have an additional task with respect to method 1, that is to somehow reproduce the geological history in order to obtain and assume a reasonable reproduction of actual over-consolidation profiles along the soil. Essentially, we propose this procedure. We have to calculate to determine in some points an undrained shear strength capacity that you want to match with this history. So we can, as we will see later, we can calculate some over-consolidating surcharge that we must add to at the very beginning stage of analysis, taking care that in that condition all the clay soil must have as drain conditions. So just having drain condition, the effective part of the stress will store the effect of past surcharge. Then we must model a second stage as well, in considering drain condition, in which we remove that over-consolidating load, and we will have an over-consolidation profile like this. After that, we are ready to reproduce what is in our soil today. So after that, we switch all the condition, the clay condition to undrained condition, and we can start analysis. Doing so, the model is appropriately initialized, and we have a suitable undrained shear capacity along all the depth along the wall. It's not simple, frankly, to calculate a good value for the over-consolidated overload, but we may try to do some trial and error, as we will discuss in the following video. Consider that if we know by sampling the undrained shear strength at some depth, we can calculate Q in order to match these values, and more or less with some iteration we may have a reasonable assumption for Q. So as long as this method can distinguish between effective stress and pore pressure, pore pressures are also an additional result of Paratie analysis, like for sands and for coarse material. And what is important to see is that pore pressure may appear even above water table and may become negative. So there may be suction, like effect normally really happens in an over-consolidation clay. Theoretically, the resistance of soil is determined based only on the internal friction angle, but the user is allowed to give an additional limit, what we call a redundant limit, and the program limit the shear stress to the lowest between the two limits. Of course, if one doesn't want to consider this additional limit, it is simply sufficient to set this limit to a very high value. In another video, we will go to with Paratie Plus and see how to do this and how to assess the results. Thank you.